So we have now talked about how to find limits graphically and how to find them numerically. And we've talked about properties of limits. And so what we have been building to is how do you find them? How do you evaluate them analytically or algebraically? And that's kind of what we're going to lead into today. You may have noticed when you were going through the properties that there was another way that we could have found the answers for some of the examples. And you might have just noticed it, and you might not have realized you noticed it, but hopefully today, what we're about to do makes sense. So first, let's jot down how we're going to do it. So when evaluating limits analytically, and you should be writing in your notebooks right now, always first try direct substitution of the target value into the function. What that means, so this direct substitution, what that means is for you to plug in C, basically. So you're going to take whatever your function is and whatever your target value is, you're going to plug it in, and you will end up with one of three things. So let's see. Let's go back to that pinkish color. If you get, so option one, if you get a number then you're done. That's your answer. For instance, what do you get for the limit as x approaches 3 of the function x squared? Well, if I plug in 3, I get 9. 9 is a number. I am finished. And if you think about that graphically, like if you were to plot this, nothing fancy is happening at 3, 9. So it should make sense graphically that if you just plug it in, the y, and you get a y value, the y value is your answer. Next, if you get a number that's not 0 over 0, then there is a vertical asymptote. At x equals c, and therefore the limit does not exist. So let's take a look at what that would be like. So let's say we take the limit as x approaches 3 of x squared plus 5 over x minus 3. So if I plug in 3 to the numerator, I get 9 plus 5, which is 14. If I plug in 3 to the denominator, I get 0, meaning the limit does not exist. Now, the reason why I wrote this not 0 right here, it's important that you recognize that a number over 0 is a number other than 0 over 0, because our third case is if you get 0 over 0, then we have to use algebra to investigate further. And graphically, I want you to think about this as like having a hole in the function. So this is a case where the limit might still exist, and it usually does. So this is a case where the limit still exists. However, algebraically, we can't get the answer through direct substitution. So we have to do more work, essentially. And this is actually something we're not going to work on today. This will be tomorrow's lesson. We're going to start. There's pretty much 4 cases of this. And 4 techniques that we use, and we will investigate those 4 over the next couple of days. So we'll do 2 each day. So first, let's just do some examples with direct substitution. So I want to evaluate the limit. Now, I can't stress enough how important it is that automatically when you start a question like this, you start by plugging in the target value. And I think once we get to some of the trickier cases, students get out of the habit of wanting to use direct substitution, and they want it to always be something tricky. And so I promise you, you will be very mad at yourself on your first quiz if you miss a question because it was actually a really easy question. You just didn't try direct substitution. So I'm going to strongly encourage you, no matter what, always plug in your target value first. So let's take a look at an example. So I want to find the limit as x approaches 1 of the square root of x squared plus 2x plus 4. So we need to first plug in 1. So I will get the square root of 1 plus 2 plus 4, which is the square root of 7. Now I want notation-wise for you to notice something. Once I plugged in 1, I no longer wrote the word limit. The act of plugging in that target value is the act of taking the limit, so you don't need to keep writing limit. So the limit of as x approaches 1 of that radical is equal to a number. It is equal to radical 7. So you don't need the word limit here anymore. Sometimes the notation can get tricky. All right, number 2, I want to find the limit as x approaches pi over 4 of the sine of x. Whew, it's probably been a while since you've done some trig. We don't do a ton of trig in this class, but I do expect that you have a basic understanding of the 6 trig functions and be able to evaluate at the special angles of the unit circle. So it is something that's kind of sprinkled in throughout the entire year. So if you don't know trig, for instance, if you did not take pre-calc last year, if you're coming from a different math class, especially an IB class, you need to let me know because you might not know all of the information you need to know to be successful. All right, so we want to figure out what is the sine of pi over 4. So I'm going to think about my unit circle. I love the unit circle. And then we know that pi over 4, I'm dividing pi up into 4 pieces. And so I'm splitting this quadrant in half. My coordinates are radical 2 over 2, comma radical 2 over 2. And I know sine is the y value. So in this case, sine of pi over 4, actually in every case when you're evaluating sine of pi over 4, you get radical 2 over 2. But the value of this limit is radical 2 over 2. All right, let's do another one. Number 3. What is the limit as x approaches 2 of x minus 2 over x squared plus 3? So the very first thing I'm going to do is I'm going to plug in 2. And when I plug in 2, I get 2 minus 2 over 2 squared plus 3. 2 squared plus 3 is not 12. 4 plus 3 is definitely 7. I multiplied in my head there. 0 divided by 7 is 0. 0 is just a number, so that is your answer. Sometimes students get confused between a number over 0 and 0 over a number. If I take 0 pencils and I put them into 7 groups, I have 0 pencils in each group. That's where that comes from. So don't let the having a 0 in the numerator throw you off. 0 divided by a number other than 0 is just 0. The flip of that, though, was the limit as x approaches 2 of x squared plus 3 over x minus 2. In this case, you would have 7 over 0. So the limit does not exist because there's a vertical asymptote. So I wanted to kind of show the difference of those two so you can keep those two straight. I am not going to show any examples of our techniques when we end up with 0 over 0, but I hope that gets you started in this section, and we will continue tomorrow. Have a nice day.